Morning. The National Academy of Engineering has published their list of the greatest engineering achievements of the 20th century. This includes the airplane, the computer, and the internet. But the number one engineering achievement above all others in the 20th century was the generation, transmission, and distribution of electricity. Now you may ask yourself, why? Why would this be the number one achievement above all others in the 20th century? Well, the fact is that this is the largest, most complex real-time control problem on the planet. The constant balancing between the generation and the demand of electricity. And if this balance is lost, catastrophe happens. In July of 2012 in India, the generation was unable to keep up with the demand. The grid became unstable, and power was lost to 20 of 28 states in India. 700 million people were without power. It was declared the biggest catastrophe in a decade. Now, this not only happens in emerging countries like India. In 2006, Eon shut down a transmission line over a river in order to let a cruise ship pass under safely. When they did that, the network became overloaded. Substations in Germany, France, Italy, Belgium, Spain, and tripped offline. Power was lost to 10 million people. So as you see, this is a delicate balance. The complexity is tremendous, and we are increasing the complexity today with the integration of large-scale intermittent generation from wind and solar, distributed generation all the way down to the home, and the introduction of the electric vehicle. So let's talk about these complexities, starting with the electric vehicle. But in order to understand that, we have to have a little understanding of how we use electricity today. Now, I would bet most people in this room know how much they pay for electricity, because you get a bill every month. But I would also bet that most people in this room don't know exactly how much electricity they use. So let's look at the average home consumption of electricity in Germany, the United States, and in France. In Germany, 3,500 kilowatt hours per year. The US, more than 3 times that amount, and in France, a little less than twice that amount. Let's look at that from a daily perspective. In Germany, a little less than 10 kilowatt hours per day. In the US, 32. And in France, 17 and a half. Okay, so how much do we pay for that? So if we look at that, in Europe or in Germany, you pay 29 euro cents per kilowatt hour. In the US, 9. And in France, 15. If we take and multiply that by our daily consumption, you will see that we're actually using or paying about the same amount in each location. So you have to ask yourself, does the price of electricity influence the consumer and how they use electricity? Okay, back to the electric vehicle. Oh, one more thing. We all know that you don't use the same amount of electricity throughout the day. At night when we're sleeping, we use very little electricity. We wake up, we turn the lights on, we make our coffee, we go to work. Depending on how warm or cold it is during the day, we use more or less. So between 1,500 and 1,900 hours is the peak demand on the grid. Remember that. Okay, on to the electric vehicle now. BMW has recently introduced their all-electric i3 vehicle. It has a range of 130 to 160 kilometers. It has a 22 kilowatt-hour lithium-ion battery. And here's the price. Remember, in Germany, you're consuming a little less than 10 kilowatt hours per day. This has a 22 kilowatt-hour battery. We plug this in and charge it. It's like we just stacked 2 houses on top of our house. If all of our neighbors buy electric vehicles and they charge it, they just stacked 2 more houses on top of their house. Do you think the grid in your neighborhood was designed to handle this load? Another way of looking at it, though, is I could charge my car, disconnect from the grid, and power my house for 2 days. But remember, we don't consume electricity evenly throughout the day. So if we charged our vehicle in the evening, and then we're able to pull some of that power back during our peak demand, we could actually lower the load on the grid by using the vehicle as a storage system. Okay, you don't have to worry about that today in Germany. 0.2% of all new vehicles sold in Germany in 2013 were electric vehicles. Now, if you look at some other countries, Norway, more than 6% of vehicles sold in Norway in 2013 were electric vehicles. Surprisingly, California, 4% of all new vehicles sold were electric vehicles. Now, in the first quarter of 2014, Germans bought almost 2,000 all-electric vehicles. Now, that doesn't sound like much, but that's nearly a 100% increase over the previous year. Okay, no one's going to buy an electric vehicle unless it can compete with gasoline and diesel vehicles. So let's take a look at a fairly basic family car here in Germany. The Porsche 911 Turbo. I'm sure many of you have these at home in your garage. 520 horsepower. It can go 0 to 100 kilometers per hour in 3.2 seconds. Has a range of about 545 kilometers, and the base price in the US is about $150,000. The Tesla SP85D, 691 horsepower. This is an all-electric vehicle. 0 to 100 kilometers per hour in 3.2 seconds, has a 475 kilometer range, and a base price of about $115,000. Let's look at it a different way, though. The Porsche has a 64-liter gallon tank. Now, I'm guessing on this, a liter of gasoline, about 1.46 euro. We know the range. So you get about 6 kilometers per euro with your 911. The Tesla has an 85 kilowatt hour battery, 29 euro cents per kilowatt, 475 kilometer range, 19 kilometers per euro. Now, let me make this very clear. If there was a Porsche 911 Turbo outside and a Tesla, I'm driving the Porsche home. You can have the Tesla. Anyway, electric vehicles will compete with gas and diesel vehicles. Okay, on to the complexity of intermittent power generation through large-scale wind and solar. Nowhere else in the world do people know this more than the Germans, as you've integrated so much wind and so much solar into the grid. So here are 2 weeks during 2014 of the actual generation and consumption in Germany. Let's look at May 10th. Okay. The nice, pretty green and light blue color and dark blue and yellow are your renewables. The ugly gray is the fossil and nuclear. Okay. If you look at Sunday, May 11th, nearly 75% of the demand. By the way, there's a red line in there, and that's the actual demand for electricity. Nearly 75% of your demand was met through the use of renewables. But on Thursday of that same week, when it was a very calm, cloudy day, only about 20 to 25% was met. This creates a lot of problems because you have to have the reserve generation in place when the wind is not blowing and the sun is not shining. Now think about this. If we could store this electricity and level this out, it would make life so much easier. Let's talk a little about storing electricity. When we think about storing electricity, the first thing we think of is a battery. So a little history lesson here. A German archaeologist found what is believed to be the first battery. It's called the Baghdad battery, simply because it was found outside of Baghdad. It was dated back to 250 BC. It's a clay pot that had a copper cylinder in it and a steel rod. When this was filled with an electrolyte, such as vinegar or grape juice, it actually produced a voltage. What would they use a voltage for in 250 BC? Certainly not to charge their cell phone. But it is theorized that this was used to electroplate gold onto other metals for jewelry or coins. Now, I must say, this is still debated today by scientists. Now, in 1800, Alexander Volta invented the electrochemical cell. It was called the voltaic pile. Obviously, these batteries are not going to be used to store the electricity that's needed on the grid. A little fact for you. The word battery was first used to describe a device that stores electricity by Benjamin Franklin. Okay, so on to the advances since 250 BC in the battery. And in 1991, Sony introduced the first commercial lithium-ion battery. There are many challenges still today with the lithium-ion battery. We know how long it takes to charge our cell phone and our laptop, and if any of you who do have an electric car, you know how many hours that it does take to charge that. Also, how many times you can recharge the battery is a challenge. It's about 500 times before the performance starts to degrade. They're very heavy, and they're expensive. A lot of work to be done by the scientists and engineers in the audience. Now, recently, I read an article out of Singapore where some researchers used nanotube technology to develop a new material for the anode. Turns out the anode is a real problem with lithium-ion batteries. With this new material, you will be able to charge your cell phone in 2 minutes. An electric vehicle will take 5 minutes to charge to 70%. By the way, 5 minutes is the average time it takes to fill your gas or diesel vehicle. So tremendous advances. But not only the speed in charging, you will be able to recharge the battery 10,000 times. That's 20 years of usage. Can you imagine keeping your cell phone for 20 years? I don't think so. Also, driving down the cost of the battery is important. And it's very important to Tesla because they want to create a family vehicle that doesn't cost $115,000. So they must drive down the cost of lithium-ion batteries. They are building what is called the Gigafactory in the United States. This factory will be 100 million square meters in size, and it will double the world's capability to produce lithium-ion batteries. Okay, there are other ways to store electricity, or energy for that matter. This is called a pump storage station. Here's one in Germany. It is the largest one in Germany. The way it works is you have water on a reservoir at the top of a mountain. And when you want to generate power, you run it down through turbines. Okay? Now, these turbines are special turbines. They're called pump turbines. They're interesting because at nighttime, when the demand is low, you actually reverse them, and they will pump the water from the reservoir below back up to the reservoir on top. This particular reservoir holds 12 million cubic meters of water and will produce electricity for 8 hours. So this facility has 4 turbines, each producing a little over 1,000 megawatts, times the 8 hours. So it stores 8.5 gigawatt hours of electricity. Now, if we go back to the graph that I showed earlier, the peak demand in Germany is about 75 gigawatts. So 8.5 gigawatt hours of storage is significant. But the important part of this type of facility is I can turn on the electricity almost instantaneously. I simply have to open the faucet, the water runs down, and it goes through the generators. This is very important when the wind slows down or clouds come in and you're unable to produce the electricity from the solar and wind. Okay. Another technique is air storage gas turbine systems. The very first facility in the world was done here in Huntorf, Germany. It was commissioned in 1978 and is still running today. There is only 2 of these in the world, the one in Huntorf and there's one in the United States. This is very, very interesting in how this works. So at nighttime, when the demand is low, it uses conventional energy to drive compressors and pumps air down into a cavern. Pumps it down to about 1,000 psi. And then when demand is high during the day, it pulls out this compressed air, mixes it with a little bit of natural gas, and drives a gas turbine. The efficiency gained by using compressed air allows you to get the same energy from less than a third of the gas that you would typically use. In this particular case, it requires 480 megawatt hours at night to compress the air, and then in the day when you need it, you can generate 580 megawatt hours. Again, this type of system can be turned on almost instantly. Okay, a little bit of knowledge about building this cavern. Okay, the reason Huntorf was selected is because it has salt underneath. And the way they make the cavern is they drill down, in this case, 700 meters into the ground. They pump water down into the ground, which will dissolve the salt, and brine comes back up until they get the cavern to the size they want. In this particular case, it was 300,000 cubic meters. All right. Now, in the United States, we're looking at this technology that had been perfected here in Germany. Excuse me. I wish this was a Weiss beer. So in the United States, we're looking at this technology and say, how can we take advantage of this? So I'm going to explain to you this proposed project in terms of how it lays out in the United States, and then I'll bring it back to Europe so you can get a good feel for the size of this thing. So what they will do is they will put a large wind farm in Wyoming. This is a very northern state in the United States that has a lot of wind. That electricity is generated and it will be transmitted down to Utah. Utah is where we have the salt flats. So we can create a huge salt cavern. 4 million cubic meter salt cavern to store compressed air. Remember, the Huntorf was 300,000 cubic meters. This will store 60,000 megawatt hours for electricity, compared to the 580 at Huntorf. And then when the people in Los Angeles, California, need the electricity because of peak demand, they will generate it in Utah and transmit it to California. So if I laid that out here in Europe, north of Hamburg would be the wind farms. They would transmit that energy to Munich, where they would store it. And then when the Romans got up and turned on all their espresso machines in the morning, you would transmit the electricity down to power those. That is the magnitude of this project. Okay, so back to the largest, most complex real-time control problem on the planet. The fact that we are making it more complex with the integration of intermittent generation from large-scale wind and solar, distributed generation all the way down to the home and the electric vehicle. So why are we here today? Why is National Instruments here today? Why are you here today? Well, our mission statement is to equip the engineers and scientists of the world with the systems they need to accelerate their productivity, innovation, and discovery. One person, one company, one country is not going to solve the problems that we have. We can do more in solving these problems by equipping you with the tools, the systems, the platforms that you need to get your job done. We impact the world more by supplying you the tools that you need. These platforms, PXI, Modular High Performance Test System, Compact Rio, Modular High Performance Industrial Platform, the most productive engineering software tool in the world, LabVIEW. We design the platforms for productivity. We enable you to innovate and discover. Now, before I close, I want to talk about a project that I've worked on for the last 2 years. This is a big data project, an Internet of Things project. Everyone's talking about big data. Everyone's talking about the Internet of Things. This is a project that actually delivers on big data, on the Internet of Things. This project was done with Duke Energy. They're the largest utility in the United States. Now, they wanted to increase the reliability in 44 of their generation plants across the whole eastern coast of the United States. In 8 different states, these plants were spread out. They wanted to instrument 50,000 assets in these plants, turbines, circulating pumps, cooling towers, motors, fans of all type. And they wanted to be able to monitor these from anywhere. If they had an issue, their expert could look at that particular facility, at that particular asset, and exactly what was happening there. They have instrumented more than 50,000 sensors onto these assets. They've deployed 2,500 compact Rio systems. And we have developed a new product jointly with them that allows them to manage this data, to manage these distributed real-time devices from anywhere. It's called Insight CM Enterprise. The CM stands for Condition Monitoring. It comes in several pieces. The Insight CM server has a thin client web-based interface that allows them to configure the devices, manage the devices, and it pulls data from the devices as it becomes available. The Insight CM Explorer allows them to go to a specific facility, specific asset, specific sensor, and evaluate exactly what is happening in real time if they so choose, or pull up historical data to see how things are trending. They can set alarms, they can respond to those alarms, and they can make a phone call and make it fixed. So again, our mission is not to solve these problems. Our mission is to provide you the systems, the tools, the platforms that you need to innovate and discover and solve the problems that we are facing today. Have a wonderful day here at VIP. Thank you.